Hello and welcome again in this discussion of fluid mechanics. So previously we have studied about the linear deformation of a fluid as well as the volumetric deformation. Now let us proceed to the angular deformation. So now let us consider again a 2D case. Okay, so any 2D case can be extrapolated to the 3D one. Okay, but that is we are analyzing the cases in a particular plane, so you can do the same analysis for any other plane and you will get the 3D result. So let us have a fluid element like this. Okay, so let me just make this a bit thinner, or okay. Okay, so this is my initial configuration. Okay, so this is the initial configuration. Let me write it. Okay, and now let us draw the final configuration. So I can draw this. No, this is not good. Okay, so this is the final configuration given by this one. Okay, so angular deformation is measured by the, okay, so angular deformation that is measured by the change in angle. Okay, so that is measured by the change in the angle between two line elements which were initially perpendicular. So strictly this is not the definition, because if the two lines are not in not perpendicular initially, then also we can define the angular deformation, so that will be the change in angle. But for the sake of definition we will maintain this. Okay, so now, so let us consider that here we must make the axis. Okay, so maybe this is the axis. Okay, so this is x and this is y, right? So at this point, so let me give it some name. Maybe this is a. Okay, so let me give some name. So this is a, this is b. Okay, this is c, this is d, and the modified one is b dash, c dash, d dash. Okay, okay, so at point a the velocity is defined by u. Okay, the x component of velocity u, and y component of velocity is by v. Okay, so this is u and this is v, the y component of velocity. At point b, that is at this point, this will be u plus del u del x into ab. So ab is del x. Okay, so here this ab is del x. So okay, uh, define this ab as del x. Okay, and this bc as or maybe AD as, okay, AD as del y, right? So this will be at point B, the x component of velocity is this and y component of velocity is v plus del v del x into this, right? Okay, so if we now have this, now let us give some name to these angles. This is alpha, this is beta, right? So I have to measure this alpha and beta. The best way to measure is the from the concept of trigonometry. So I can apply either of sine or cos. Okay, so now let me drop some perpendicular from B to AB. I mean from B dash to AB. Okay, so this is the perpendicular, and maybe this point is E. Okay, that means from triangle A E B dash. Okay, so this gives us tan alpha is equal to B dash E by AE. Okay, so now what is B dash E? Okay, so B dash E is after maybe time delta t. So this configuration is at t and this is at t plus delta t. Okay, so after time delta t, A will move how much in vertical direction. So this is movement of point A is in time delta t is v delta t, right? And movement of point B, okay, so that will be what? So that is it has to go on, so it has gone to B dash and actually A has gone to A dash. Okay, so this is this is not compulsory that this two configuration has to meet in this point. Okay, that is this whole deformed shape, this A and A dash. So in this diagram A and A dash are coinciding, but that is not necessarily the case. Okay, so now movement of point B to B dash, that will be what? V plus del V del x into del t, right? Because the y component of velocity, okay, so I should write this as the movements in y direction. Okay, okay. So if I have this, so now what will be the B dash E? So then this V dash E will be, okay, so this B dash E will be the movement of B, right? Movement of B in y direction minus movement of A in y direction, right? Because initially they were both in the same level. Okay, so now this will be what? So movement of B is this one minus this one, right? So this will be what? This will be del V del x del x del t. Okay, now we have this. So now let us find AE. Okay, so what will be AE? So AE is uh, now initially this is, so the point, the horizontal distance between point B and A was delta x, right? Now we have to find the modified length, right? So this will be some delta x plus some change. Okay, so this some change can be positive or it can be negative. Okay, so this is the same problem. So movement of a, okay, movement of a in x direction, that will be what, u delta t. And so movement of b in x direction, that is what, u plus del u del x into del x, right, delta t. Okay, so now the final length will be what? So this is the same problem, right? So I mean same problem as the linear deformation. So if I have this as my initial length, so this was AB, right, AB. So maybe A has moved to this position. Okay, so let me take some another color. So maybe A has moved to this position and B has moved to this position. Okay, so this is now A dash and B dash, horizontal, only horizontal movement. So this is what, this is u delta t, and this is what, this is u plus del u del x, this into delta t. I have to find this A dash B dash, right? And I know that this is what, this is delta x, right, minus u delta t, right, because AB is delta t and this part is u delta t. Sorry, I mean AB is delta x and this is u delta t, so this is delta x minus u delta t, right? So A dash B dash is clearly from the geometry del x minus u delta t plus u plus del u del x, right? So this was delta t, so this will be delta t. Sorry for the silly mistakes, I sincerely apologize for that. Okay, so del x minus u delta t plus u delta t plus del u del x delta t. So this is being cancelled out. So A dash B dash is del x plus this amount of change, right? So now, so I am taking the limit delta t tends to 0. Okay, taking the limit delta t tends to 0. Okay, so in this limit delta x will also tend to 0, and that is why the multiplication of two small numbers will make this term almost negligible. Okay, negligible. So A dash B dash is almost equal to del x, that is AB initial thing. So here also this AE, so here this AE was equivalent to A dash B dash. That means now BE I have got, so B is this, I mean B dash E, and AE is almost equal to the initial del x, right? That means tan alpha. So this was the thing. Let me write it here. Tan alpha is equal to B dash E by AE. Okay, so B dash E was what? B dash E was this. So B dash E is del V del x del t, and AE is almost equal to del x. Okay, now for delta t tends to 0, alpha is very small, right? And that directly means if alpha is very small, tan alpha is almost equal to sin alpha, and that is equal to almost alpha. Okay, so that means alpha is equal to del v del x. Okay, so delta t. Now that is actually alpha is the change in angle, right? So let me uh, write it delta alpha, because alpha in this case initially was 0. Okay, so Now limit, I have applied the already the limits, so I don't have to write it again and again. So this will be del v del x. And what is this? So change in angle, right? So this is the angular strain rate, okay, angular deformation rate actually. So the angular deformation, okay, or the angular strain rate, right? Similarly, so this is basically the alpha dot equal to del v del x, right? So alpha dot equal to del v del x, because in solid mechanics also, if you have to find the angular strain rate, you are supposed to find the change in angle between the between two line segments which were initially perpendicular. So the same concept is applied in case of fluid mechanics also, okay. Similarly, if you term this angle as beta, then this will come as, this beta dot will be du dy. So this is your uh, this is your homework, you have to derive it, okay. So now by definition I have to take the average of these two. So by definition, angular strain rate is equal to alpha dot plus beta dot by 2, okay. So that will be half into del u del y plus del v del x, okay. So this is true for any one plane, okay. So now, and in index notation I can write it as half into del uy. So if it is u and v, okay, so u is equivalent to u1, v is equivalent to u2, y is equivalent to x2, x is equivalent to x1, okay. So it is essentially del u1 by del x2, right? So this is the actual case. So del, and then del uj plus del x, this I, okay. Now for xy plane, so for xy plane, let me uh, make you, so let me make it more simpler, okay. So for xy plane, for xy plane, right, that is what, I equal to 1 and j equal to 2. This boils down to this half into del u del y plus del p del x multiplied by half, right? Okay, so for maybe yz plane, it will be different, okay. So this was the angular strain rate. Now let me come to the rotation, okay. So rotation part, okay. So rotation part, how can say this? So let me refer to the same diagram, okay. So if I can copy this, let me see, okay, copy, okay, there is option, but I don't know that why I cannot paste it, okay. So let me try it, just, okay, now I have pasted it, now this is perfectly fine, okay. So for rotation, the the measure will be the, I mean, given by the angles alpha and beta, but now the definition is average of the angular velocities of, okay, of two line elements initially perpendicular to each other, okay. So then it will be what? Now let's see that for this case, this AB has been rotated in this direction, right? But this uh, AD, this line segment has been rotated in this direction, right? So this definition essentially boils down to half into, okay, alpha dot, or maybe I should write that omega of AB plus omega of what, AD, right? So this is nothing but alpha dot and minus beta dot, because these two are having rotations in opposite directions. So this is del u del x. Okay, so alpha dot is y, sorry, I have written it wrongly. So alpha dot is del v del x, right? So del v del x minus del u del y. Okay, now so this is what, this is omega z, that is angular velocity about the z axis. So similarly, if I have to write this in index notation, then omega is equal to half into del uy del xj minus del uj del xi. Okay. Okay, so now you can make an argument, that is I could have write beta dot minus alpha dot. Yes, you can. Okay, so this just depends on your choice of the reference frame. Okay, so if I have taken this, the sense of rotation of AB is as positive, then I have to take the sense of rotation of AD as negative. You can take the vice versa case also. Okay, but the magnitude will remain same. Okay. Okay, so now let me tell you another thing. So then this omega, this vector will be omega x I cap, or I can write as omega 1 e1 cap. So by this time you should be conversant with this e notations, because these are just, this e1 is I cap, e2 is j cap, and e3 is k cap. Okay, now so this, if I expand this, this will boil down to, okay, omega 1. So omega 1 means omega x. Okay, so let us see how can we find this. Okay, so if I have a 2D velocity vector, okay, 2D velocity vector, okay, that is v is equal to u, okay, so u e1 cap plus v e2 cap. Okay, or let me now write, okay, this is fine. Then if I do something called this derivative, that is, okay, so this I cap, j cap, k cap. So I cap is just 2 bit, okay, and this will be u, v, and 0 component, right? So this will be what? Let us see. So I cap into this into 0 0 and del v del z. So v is the y component, so this is also 0. Okay, so plus j cap, actually is minus j cap into is 0 and 0. So this is also 0, and k cap into del v del x, right, minus del u del y. Okay, so actually this also should not be there. Okay, this is a 2D, okay, 2D thing. So v is not a function of z. Okay, v is only the velocity in u and v are defined in only xy plane. Okay, so this essentially give you, this is giving you the this thing, right, omega z, 2 into omega z. So this is 2 into omega z, and this operation is nothing but curl of v. So those of you who have studied the vector calculus, the curl operation, they can relate it, right? Okay, so this is a 2D thing. So so this component should also not be there. Z component is not necessary. So in 2D thing, why these things are 0? Because maybe, I mean, if I am saying that something is 2D, that means the variation in the other direction is not significant. Okay, so that is why del z of anything is equal to 0. Okay, so further you will see that many 2D situations, or many 3D situations, we will simulate or model as a 2D situation. Okay, so this is actually the curl, and this curl of V in terms of fluid mechanics, this is very important. This is called as vorticity omega. So this is vorticity. Okay, so by now you know that this vector is uh, so by now you know this vector is half of vorticity, that is curl of V, that is half of vorticity vector. Okay, so okay, that means if curl of V is equal to 0, then the flow is irrotational. Okay, irrotational. So rotation means rotation about its own axis, rotation of a fluid element about its own axis. So if curl of V is not equal to 0, that is rotational. Okay, okay, okay. So now we have studied the angular deformation and rotation, right? Now let me define one more thing. So now by now you know that what do I mean by velocity gradient tensor, I mean tensor actually. So let me define a new tensor, that is velocity gradient tensor, right? So velocity gradient tensor is defined by del uy del xj. So how many free indices it is having? 2, right? So 2 free indices. That directly means it is a second order tensor, right? Then it will have, so how many components? So for I 3, and for every component of I it will have another j equal to 3. So that means 9 components. So this will be a 3 by 3 matrix. Okay, okay. Now this is also, so this matrix can be written as half into, okay, del uy del xj plus del uj del xi plus half into del uy del xj minus del uj del xi, right? Okay, so essentially this is a symmetric part. So this thing you have studied in your matrix algebra also, that then that is a matrix can be divided into a symmetric and a skew symmetric part, right? So this is a skew symmetric part. This is the skew symmetric part, right? Also this part denotes the deformation, right? I have told you that this is deformation, not specifically linear or angular. So sorry, so if I equal to j, then it will be linear deformation. So it is your task to verify and make yourself understand. Okay, so I equal to j means what? So this will be what? Half into del del I del x plus half into del I del x. So if I equal to j equal to 1, okay, then it will be what, half into 2 into del u1 by del x1, that is linear deformation or linear strain rate in the x direction. Now I think it is clear. And if I not equal to j, then it is angular deformation. Okay, similarly this part is rotation. So this is essentially is the angular velocity. Okay, so this is the omega. Okay, angular velocity. That means velocity gradient tensor contains both the information of this deformation and rotation. Okay, in continuum mechanics also we have the same concept for solid, but in fluid mechanics we have the concept of velocity, while in continuum mechanics we have the concept of uh, the displacement. Okay, and why it is so? So for solids mainly, solids can, I mean generally solids do not flow, right? So they have a particular displacement even after a long amount of time. Okay, and that will happen after a particular after the application of a certain amount of force. Before that it will not happen. But in case of a fluid, the fluid will continue to flow even if under the application of an infinitesimally small shear stress. Okay, so because of that fluid will have a continuous strain or displacement, and that is why it is not important to measure the displacement or strain of a fluid, but it is important to measure the strain rate or the displacement rate of a fluid. That is why we use uh, the displacement per unit time, that is velocity in case of fluid, and the important parameter for solid is the displacement. Okay, okay, so velocity gradient tensor. Okay, so after this conception, so if a situation can be given if, in any question, if I give you the v, the u and the w, okay, then my first question will be that if the flow is rotational or not. Okay, rotational or not. My second question will be that maybe in z plane, I mean in zx plane, maybe in zx plane, okay, show the uh, deformation or show the configuration of a fluid element initially in rectangular configuration. Okay, initially in rectangular configuration. So this is easy. We have to find the curl, right? If curl is 0, then rotational, then irrotational. If curl is not 0, then rotational. And this will be, you have to find both the uh, deformation part, that is you have to find this del ui del xj plus del uj del xi for z means I equal to 3 and j equal to 1. For 3 1, that means u3 means what? So let us understand it deeply. U3 means w, and x1 means x, u1 means u, x3 means z. This, so this will give you the deformation, the angular deformation. And for the linear deformation you have to look for, so this will give the angular deformation, angular, right? So this will give you the angular deformation, right? So if this is equal to 0, Okay, so if this is equal to 0, then no angular deformation is happening. Okay, and now how can we, so this is check for angular deformation. Okay, check for, and now this is check for rotation. So check for rotation will be similarly half into del uy del xj minus del uj del xi. Okay, so this will be similarly half into this minus this. Okay, so if this is again 0, then there will be no rotation, and if this is not 0, then there will be some rotation. Okay, so again this is for I equal to 3, j equal to 1. Okay, now checking for linear deformation, right? So this will be what, the same expression, because deformation is given by this expression, right? Okay, so now I equal to j equal to 1 to see the deformation. So this will be a check for linear deformation in x1 direction, and for I equal to j equal to 2, so this will be the linear deformation in x3 direction. So this is 3. Okay, because we are talking about the zx plane, so we have to look for both the x the linear deformation in x direction and the linear deformation in z direction. Okay, so if maybe this is coming as 0 and this is coming as non-zero, then this will happen and this will not happen. Okay, now maybe so you have told that the initial configuration is rectangular. So now first draw the zx plane. So this is x and this is z. Okay, so the initial configuration is something like this, that is this. Okay, initial configuration is something like this. Now the modified configuration, so now let us take some cases, and your task will be to draw the another cases. So if the angular deformation is not 0, and also the, okay, the angular deformation is not 0, okay, but the rotation is 0. Okay, so here I am taking as angular, let me write it in another color. So 1, angular deformation is not 0, 2, rotation is equal to 0, 3, linear deformation is not equal to 0. Maybe this is the case. So angular deformation is not equal to 0, then this will deform like this maybe, and this will also elongate. So if this is AB, okay, so let me give some name. So ABCD, so AB will angular, so AB will have an angular deformation as well as some linear deformation. Okay, so linear deformation can only happen for AB in x direction. Okay, because AB is aligned with the x initially. So now maybe AB will look like this, so it has elongated, or maybe it maybe like this, because linear deformation can also mean the compression. So maybe this is AB dash. Okay, so now again after linear deformation, maybe this is the case that a point has moved to here. Okay, so another option is this, that is maybe I am having my a line now here. Okay, it is here. Okay, and maybe now this AD, okay, AD has become like this maybe. Okay, it has been elongated along, and now CD will be like this, anything arbitrarily. You have to just show the qualitative nature. Okay, Okay, so maybe this is A dash, B dash, C dash, D dash. Now let us let us take another case. Okay, just let me copy it. So copy and so paste. Okay, so I have pasted it. So now let me remove it. Okay, so now maybe the case is, so one is angular deformation is 0 and rotation is not 0, linear maybe is not 0. Okay, so then I can readily see that there will be some rotation. So if this rectangular rotates, okay, then I can draw it maybe like this, right? Okay, now see that the angles will not change, right? Because angular deformation is the measure of change in angles. Okay, so the angles will not change, right? But linear deformation can be there. So this is A, I mean A dash, B dash, C dash, D dash. So A dash, B dash maybe is not equal to AB. Okay, and it has also rotated by theta dot. Okay, so angular deformation is not there. It has been rotated like a rigid body maybe. Okay, so this is the thing. Okay, so now let me go for another concept, that is the vortex. Okay, so I will just define what is a vortex and what are the two kinds of a vortex. Okay, so vortex flows, so these are very interesting. So vortex flows means flow revolving, okay, revolving around any axis, or fluid flow, or fluid that is revolving around any axis. So don't confuse it with the rotationality. So rotationality means rotation about its own axis. So rotation of a fluid element about its own axis. So just just think of a giant wheel in the fairs. Okay, so in the giant wheel, so maybe in the giant wheel, what happens? So there are some compartments, some little compartments in which we sit, right? And then the total wheel rotates. So there can be two types of cases. If the compartments are rigidly held with the uh, large beams, okay, with the large cantilever beams, if those compartments are rigidly held, so then those will not swing when the giant wheel is rotated, right? But this is not the case in practical. The compartments are not are I mean rigidly fixed. They are allowed to rotate about a particular axis. Okay, so when the wheel rotates, then along with that rotation, those compartments actually make their own swings about their own axis. Okay, so what I am trying to say is, if this is the center and if this is the center and I have the compartment here like this, okay, so maybe this compartment can rotate about its own axis, about this axis. Okay, and also this is having a rotation about this axis. So having the rotation about this axis is ensuring that it is a vortex flow, and having the rotation about this axis is ensuring the rotationality. So a vortex flow, a vortex flow can be rotational as well as irrotational, right? So you just replace those compartments in the giant wheel with the fluid elements, okay, and that will give the definition or the analogy for the vortex flow and the rotationality. So readily then I have seen that the vortex flows can two types of rotational vortex, okay, rotational vortex, and so this is another name is the free vortex and forced vortex, okay, free vortex and forced vortex or irrotational vortex, sorry. So rotational vortex is the, I'm extremely sorry, rotational vortex is the forced vortex, and free vortex or irrotational vortex, okay, so free vortex or irrotational vortex, okay. So we will derive the expression of velocity, or rather I will now tell the expression of velocity, and later from the conservation of momentum and all the things we will derive those things, okay. So this rotational, I mean this force vortex is like the, is analogous to the rigid body rotation, rigid body rotation, that is it is having some angular velocity, and the velocity field is given by u theta is equal to some constant into r, that is the radial distance from the axis about which the fluid body is revolving, because that is the basic definition of any vortex flow, and ur is equal to 0, and this has u theta 1 by r variation and ur equal to 0, okay. So your job is now to calculate the curl and to verify if the force vortex is rotational or not. So for forced vortex, okay. So for forced vortex, let us see that the curl of velocity vector, okay. So for forced vortex, the curl of velocity vector will be what? So this will be now E of, so in ijk, that is x y z. So in cylindrical in r theta z, so from x y z I have to move to r theta z. So this will be er e theta e z, the unit vectors, and this is del del r, okay, del del, I mean del del r into del theta and del del z, and this is, so this is what this is. Now for forced vortex u theta is so u r equal to 0, u theta equal to c into r, right, and what, so then this is 0, right, uz is 0, right. So actually here also the del del z is not important, okay, because the variation in that direction is not considered, I mean in z direction nothing is varying, okay. So this is actually not important. So again we have what, this, so this will have something as a constant, okay. So this is not equal to 0, so this is rotational, and for the free vortex this will be c by r, okay. So now this will be your task actually, and actually what happens that this this will have some in bracket r into this thing, okay. So this is the actual I mean, in cylindrical coordinate, the variation is del del r into v theta. Okay, so that will be what, r into del v theta del r plus v theta into 1, right? So this will be the actual derivation. I mean actual r theta z, uh, I mean r theta z del operator. So this del in Cartesian coordinate, this is del del x plus j del del y plus k cap del del z. Okay, and this will be changed in any other coordinate like r theta z, that is the cylindrical coordinate, and r theta phi, that is the spherical coordinate or the polar coordinate. Okay, so the thing is, there is no glory in I mean in mugging up or remembering this expression of this del in various coordinates. Okay, because that you can find from any book, or maybe in good institutes those will be given, because there is no, I mean, no intelligence in mugging up these expressions. Okay, but you have, I mean, you should have the concept that is curl of v will dictate or will govern that if the flow is rotational or irrotational. In any interview also, they will ask just, they will maybe first ask that which vortex flow is rotational or irrotational. Then you will say that the free vortex is irrotational and the forced vortex is rotational. Then they will ask that how you know that. Okay, so you know that by calculating the curl. Okay, if you say this, then that is enough. Okay, so now you can say that yes, I don't recall the expression of this nabla operator, that is what will be this and this, but I know that if the curl, if you give me the expression of nabla operator, which is not the field of fluid mechanics but mathematics. Okay, I mean the understanding of fluid mechanics has nothing to do with the nabla operator. Okay, so in this case, so I will say, I will now take up these two vortex flows in the next class, and will present a very detailed analysis on each of this, that for the, and I will define a new parameter called circulation. Okay, and how the circulation and the vorticity is correlated by Stokes theorem, I will say that. Okay, and there are some another very beautiful features of forced vortex and irrotational vortex. Along with that, I will give you some practical examples. Okay, of, I mean, in daily life we see the forced vortex and free vortex in our daily life. Okay, at least 3 or 4 times in a day. Okay, so with that, I will now stop, and if you have any doubt or any issue with the learning, you can tell me in the comments. I will try to solve them. Okay, and just keep learning and message me if you have, in comments, if you have any doubts or any issue regarding anything. Okay, I will try to serve you best. Now, if I am not the person who can tell you or guide you in that matter, then I will contact with any other friend of mine who is expert in that, or maybe my senior, or even any of my teachers. Okay, so I can make some videos with them to solve your doubts. So feel free to comment, and until the next video, take care of yourself and goodbye. Thank you.